Today's lesson from section 2.6 on special functions begins with being able to write, graph, and apply special functions. And the three types we're going to be discussing are piecewise, step, and absolute value functions. So let's get started. Piecewise functions. You should have seen these before. Probably didn't spend a lot of time on them, but different function rules for different parts of the domain. So if you look, you can see that we have three different functions. F of x equals 3x, f of x equals 6, f of x equals the opposite of x plus 10. And along with that, they are each graphed over a different domain. So with that, we're going to begin by graphing. As you know, f of x equals 3x stands for the result, the outcome, as we say, the y values. So y equals 3x is one of the equations we want to graph. Y equals 6 is one of the equations we want to graph. And y equals the opposite of x plus 10 is the final equation. So knowing that, you should be able to look at all of those and start saying, okay, what are they? And by looking at their equations, we should be able to tell that they're all linear. First one happens to be a line with a positive slope. Second one is a line horizontal. And third one is a line with negative slope. And now the only thing is to graphing them, we can't just graph the three lines because we have portions and pieces. So we can only graph, when we're looking at the first one, we can only graph the pieces of the line between x equals 0 and x equals 2. So our very narrow strip of where we're going to be graphing falls between those two x values. So here we go. If we started graphing that one, we'd say, okay, well, the slope is 3, or 3 over 1, and the y-intercept is 0. So we can start right at the y-axis and start with 0, but notice that it says we want all the values greater than 0. So we are not going to include the 0. We're going to make it an open circle. But then we're going to move up 3, 1, 2, 3, and over 1. That's in our range, so we're going to place it. Up 3 over 1 in our range and place it. So we now have 2 points off our line, and it can only be in that range, and we want to make sure by connecting. So our first equation, the only part of the line we can draw is that. Second part, we're going to graph only between 2 and 4. So now our x values are going to come anywhere between these two x and y's. So we've got y equals 6. You should know y equals 6 is a horizontal line. It has 0 for a slope, and its y-intercept is 6. So we will graph a horizontal line going from 2 to 4 inclusive. Here's 2, here's 4. And we would stop right at 4 for the next portion of our line. Then we look at our third and final one. Our line has to fall between 4 and 6. So down in this area, all the portions of the line that fall between 4 and 6 would be what we need to graph for this example. So y equals the opposite of x plus 10. A good choice for some people in this case is to graph those extremes, those x values that fall on the extremes. So we're going to start it down at 2, and we're going to end at 6. So if we put a 2 into this equation, the opposite of 2 is negative 2. Negative 2 plus 10 is 8. If we put 6 in, the opposite of 6 is negative 6 plus 10 is 4. So we get 2, 8, the low end. 2, you know what? That's supposed to be a 4. So let's quickly change that. We'll do that over here. And then we will change our ordered pair here. And so we'll put a 4 in. The opposite of 4 is negative 4. Negative 4 plus 10 is 6. So now looking at that, we have 4 and 6. as our low end. So here's 4, 6, so it's going to start right here, and then from 6, go up 4, 1, 2, 3, 4, going to end right here. The end of our graph starts up on a steep slant, goes horizontal, then comes back down, and that would represent a piecewise linear graph. Each rule, each function rule determines a new piece or portion of this graph. That's all for piecewise graphs. Let's move to step functions. And in the step function, we will be graphing two different types of steps, and they usually come from either the greatest integer function, which is known as the rounding down function, or the rounding up function. So it deals with whole numbers. You're not thinking of rounding necessarily on fractions and decimals. You are. So you are going to have to make sure that you do incorporate all x values here, or you may end up with an incorrect graph. Now, the difference in the symbols. You can see that for the rounding down function, your little corners are at the bottom. That's probably the most popular way and symbol to use for a rounding down function. This is also by some textbooks, and it's actually used in our textbook a little, so be careful of that. On your tests and quizzes, I'll be using the bottom one, the bottom cornered symbol. Then there's also for the rounding up function, same exact thing, but where the corners are at the top. So basically your corners extensions are showing you where you're rounding, up or down. Okay, now in a rounding up or down situation, you definitely want to incorporate not just whole numbers, but fractions and or decimals as well. So let's start with, we want to include some positives, some negatives, and 0. So if we did that, maybe if we, and we might have to continue our XY table over here because we don't have enough room. So if we put in 2 for x, then maybe we'll put in a decimal in between that. So some people would say, okay, what about 1.5? Then we'll go down again, we'd be at 1. Then maybe a 0.5. And then 0. And then we go to the negatives. Negative 0.5. Negative 1. Negative 1.5. And then negative 2. So we've got a whole series of points and decimals that fall in between them, so we can see what our values are. All right, let's do the whole numbers first because they're a little easier. And we would get 2, put it in first, do the rounding down. So 2 rounding down, rounding up is what we're doing. Rounding up function would still give us a 2, but half of 2 then is 1. So whenever we put in a 2, we get a 1 for this rule. Go down to the 1, next whole number, rounding down function doesn't take us anywhere. Half of 1 is 1/2 or 0.5. Next whole number, 0. Half of, or rounding down function does not affect it. So 0 times a half is still 0. Next whole number, negative 1. Negative 1 times rounding down function does not, rounding up function does not affect it. And then times 0.5 is negative 0.5. Negative 2, rounding up function does not affect it. So negative 2 times a half of negative 2 is negative 1. Okay, now the next one's your choice. You can work with decimals, fractions. I think I'm going to just remind you about how to work with fractions in this case. So let's go to our 1.5. If we do 1.5, that's 3 halves. Okay, and then you're supposed to do the rounding up to it right away. So you're not going to do the multiplication, you're going to do the rounding of 3 halves. So 3 halves is 1 1/2, rounding up would make that a 2. Half of 2 is 1. Then go to the 0.5, or 1/2 again. Rounding up function becomes a 1. Half of 1 is 0.5. Negative 0.5, rounding up, remember up is to the higher, would make that a 0. Half of 0 is 0. Then go to your negative 1.5, rounding up would make that a negative 1. Half of negative 1 is negative 0.5. So now you have some things established so that you can go to your graph and see the pattern, make your step functions from there. We'll do that next. One comment though. If you just pick x and y's in a random order on step functions, you tend to cause yourself great headache. You can't see the pattern. You can't see where things are changing in the steps. So I would highly recommend you stay consistent, stay consecutive in the choice of your x values for step functions. All right, from here, if we're at 2 over 2, we were up 1, so we know we're going to be there. If we were at 1.5, so half, we were up there also. If we were at 1, we're at 0.5. So we want to say anything between here. Ooh, that doesn't look too open. A little harder. Maybe we should, let's erase this again, start over, and let's make them a little smaller. That might help me in terms of graphing. Might be able to draw an open circle. All right, so 2, 1 would have been solid. 1.5, 1 would have been solid. But the 1 is at 0.5. 0.5 is there. I need an open circle here, and then everything over here with a solid. So I've checked off these two are graphed. We're now going to graph 1 and 0.5. When I'm over at 1, we're at 0.5. Well, this is going to be tough. They're awfully close together. I would have a closed circle here, all the way over here. So it would have been open, come back here, close. Probably should have counted by 2s, or each line was a half or something. But that's making it a little crazy. Let's make one more change, and let's say we've got x values of 2. I don't have all the x values of 2 here. Well, let's just finish the way we're going. If I have a 0, it stayed at 0. But if I had any point over in here, so I now have open circle here, everything this way, solid. And then next one, anything between negative 2 to 1. And then last but not least, that's an open circle. So this would be open at, oops, you can see I screwed that up. Went over too far when I did that. One more time. All right, we've got negative 2 and 1. There we go. Now all the points between 0 and 1 were at a half. Got those done. Oops, got those done. Now all the points between negative 1 and 0. So open circle. I think I had that one correct. Okay, the next one, all the points between negative 1 and negative 2 are at a half. So open circle, closed. And now all the points between should be at -1. So we have this pattern established. Once you have it established, you don't have to do dot, dot, dot. My open circles on the left, my closed circles on the right. The only change I would have made here was to probably make my intervals a little bigger, maybe count by each 2 spaces is a half or something like that, just so you can not have it so compact. All right, bring any more questions you have about graphing, rounding down or rounding up functions, which we did here, to class, and we'll discuss intervals is the key. Absolute value functions are the third and final one. F of x equals the absolute value of x can be defined as follows. If you have the absolute value of x, and x is greater than or equal to 0, on absolute values, you know, the absolute value of a number can be positive. So if you're putting a positive number in, you will get out exactly what you put in. However, if you're putting in a negative number for x, you will get out the opposite of what you put in. So keep that in mind. And we want to graph the absolute value of the absolute value of x times 2, and that's f of x. So again, we probably want to make an xy ordered pair just to see where our values are at, to include a couple combinations. And I will extend it over here because we probably won't have enough room to show all our points. All right, let's go. -2, -1, 0, 1, and 2. We've only used whole numbers, but we use positive, negatives, and zeros. Absolute value functions, you can put in fractions if you so choose. You would still get positive numbers, positive, negative numbers would turn to positive when you take the absolute values. Here we go. Put in a -2. Remember, we're putting it into the absolute value of x times 2. So take the absolute value of -2, you would get 2. 2 times 2 is 4. The absolute value of -1 is 1. 1 times 2 is 2. Absolute value of 0 is 0. Times 2 is 0. Absolute value of 1 is 1 times 2. Absolute value of 2 is 2 times 2 is 4. So you can see our ordered pairs. And if we continued putting other x and y values in, fractions, decimals, we would have more values, but we have enough here, so let's go. We would graph -2, 4, -1, 2, 0, 0, 1, 2, and 2, 4. What you should see here, the board looks like it's a little off, is a V-shaped graph when you are finished. And probably the thing to remember mostly with absolute value is when you say absolute value, think of that as a big V, because you only have upward or downwards V's when you graph. So absolute value, when you graph those, you should always be looking at some sort of V. So those were our 3. Now here's a real world example of where we would use some of these functions. But this is a formula that was in the book, so take a look. The relative error in a measurement of an object gives the amount of error in the measurement relative to the true measurement. If the true measurement is x of t units, then the relative error r in the measurement, x, is r of x equals, you will take the absolute value of the true measurement minus the relative, the measurement x, and you will divide it by the true measurement. So we're going to use that. It's in the book. Not that it has to be memorized, but it does have to be used since it does relate to what we're discussing. So we're starting here. We've got a certain machine's part's true length is 38.9 centimeters. Its length is measured as 39.25 centimeters. Find the relative error in the measurement. So knowing that, we would go back to, if we don't have it memorized, the formula. We we're supposed to be looking at for this one, and that would be the relative error. And we would put in the values given and find the relative measure. So here we go. If we set a certain part's true length, so that's the x of t, that's 38.9. And that goes down below as well, you can see. And we want to subtract that from its length that it was measured. Absolute value bars around that whole thing, and that is supposed to give us the relative error. So if you complete that, do your math, we should be able to see in class if we have any issues with using that formula as a real-world example. So that, along with any questions from the 3 different types of graphs, is what you want to bring to class for discussion. That will be all for today.